Last week we discussed the hyperbola, right? And I think I mentioned about the quiz, right? Quiz will be on not this week, next. Today is 1 March, so it should be on. So quiz will be on. Okay. So not this week. Okay, next Tuesday. So today I will continue the polar, the conic section, but in polar. Maybe finishing all the parts in today's lecture. And if we still have time, I will go to chapter 11, okay, for today, just a short. And next Thursday, on the first half, still chapter 11, but the other one will be reviewing chapter 10. Okay. And then next week, Tuesday, we have chapter 10 quiz. Okay. So it will be on chapter 10. Okay. All the topics will be on chapter 10. And please check the video that I attached in the Moodle. That's example practice on, especially on calculus in parametric and calculus in polar. Okay. Okay, so let me finish the chapter 10 with 10.6. Okay. So this will be conic sections in polar coordinates. Okay, so let me start with the theorem. Okay. Let f, a focus, be a fixed point. Or a focus. And L, this is usually a directrix. Be a fixed line in a plane. And then we set up some positive number E we call this eccentricity. And then we will have PF divided by PL, or the ratio where P is a set of points. Okay, P is set of points, set of all points P in the plane such that this is a conic section. So I hope you get my point here. This is the definitions of the. So we set up some definition here. We know the focus, we know the directrix, and if P is set of point in those planes, and we have the ratio of the P to focus over P to the directrix is some kind of a positive number. We call it eccentricity. So if this exists, then this all points P is on is a conic section. We can say that. Okay. So we can say that P, or any point P that are included in this equation, then the shape of that P will be a conic section. Okay. And what conic sections, what types? We will have different types, right? We will have an ellipse. This is if E is less than 1. We will have a parabola if E is equal 1, and hyperbola if E is greater 1. Okay, so this is the definitions. So I think we can take some time to understand why we need this and what can we do, okay? And then how we can get the informations or the proof. And later, through the number E, we can also can create the polar conversion from the conic sections. Okay. So all the conic sections will have their counterpart in polar. Okay. Okay. Let me draw the the diagram or the schematics for the picture. Let's say this is the axis. This is Y. This is X. Okay. And let's say this is a directrix. Maybe a little bit closer. This is L, or directrix. Okay, and then let's say our conics is here. Well, it can be ellipse, it can be hyperbola, it can be parabola. Okay. And let the point here becomes F, okay? And then we have the distance from directrix to the y-axis. This will equal D. Do you feel hot? Do you need to turn on? I think can someone over there help to turn on the air conditioner? Do you think the window is open over there? Can you close it? The one? Yeah. Is it on? Is it on? I think the yeah, this one. Yeah. Yes, yes. Yeah. Make it maybe 20 or maybe 20 or 19 or 21. I think it's still 21. Okay, let me just draw first. Okay, let's say we have some fixed r, the radius here, and then we have an angle around here, and we can take this into a triangle like that. So we will have a distance here in the triangle, the sides of the triangle. This will equal with the r cosine theta. And our directrix, since the distance from the focus is d, or from the y-axis is d, we can write this as x equal d, right? Okay. Let me write that the PF, the distance from P to F, is a radius r. And PL is, so from P to L, so here, in here will be d minus r cos theta, right? So this is d minus r cosine theta. Okay, so if P, so maybe let me write here. If P has polar coordinates that is r and theta, okay, we can convert the distance on the Cartesian into polar, okay, by using the r and d. And then we have the conditions, that is, we have PF over PL, right? That is equal with the E, or in our case is eccentricity. Okay. And further, we can take this and write in this equation. And let's substitute all PF and PL with the polar. Okay. So PF will be R, and E and PL, E is still E, PL will be D minus R cosine theta. Okay. Okay. Okay, let me continue in the new slide. Okay. So let me write here And then what we are going to do, we squared all of this. We squared. And remember that r squared is our circle, right? Circle equations. We can convert them into xy. So let's convert to see what this looks like. And r cos theta is equal x, right? So we can write this in terms of d minus x and then squared like that. Or we can write this and we expand the quadratic. And then let's move the e squared x squared to the left side. And we group x squared like that. And then the other one is plus 2 e squared dx. And then plus y squared. And the last one will be the e squared and d squared. Now if we look here, we have x squared and x, right? We can complete the square. We can complete the square. Either you divide by 1 minus e squared to all of the numbers, or we can or maybe we can divide by x squared plus 2. Maybe write d first so that it can be easier to see. Okay, now from here we have x squared. Let me write in, maybe here, plus 2, or maybe d squared. This is 2x. We can write this in terms of x plus e squared d over 1 minus e squared, right? Divide by 2, right? If we check, x squared plus 2e squared d 1 minus e squared plus e squared d 1 minus e squared, this having squared here, right? So we need to plus the other side with plus plus the other side, so we can write this one plus y squared This will be 1 minus a squared and then squared. Okay. Now, if we look at this, or let me write in a different color. Now, we have E on all these three components. Okay. This E can be equal 1, so E can be greater 1, can be equal 1, or less than 1. If E is less than 1, it should be an ellipse. The ellipse is, if we still remember, this will turns out to be, let me just write first the ellipse and then we see how will the two will be connecting. This is the ellipse, right? Okay. So first, we can check if E is less than 1, it will be turns out to be ellipse. It should be like this, right? Based on our definition at the beginning. And then we can define each of the terms. That is the H, the A, and B. Okay. Now the H will be the terms in, so the H, let me write here, will be our minus E squared D divided by 1 minus E squared, okay, from the equations, from what we have implying in the equations. And then A squared this will turn us out to be the one on the right side. This one. Okay, because we divide all with this equations, right? So that it's become 1, right? So we need to divide this. So A is the same as the right side fractions. And then B squared will be the 1 minus E squared, right? 1 minus E squared, we need to divide by the right side, so we are canceling this squared here for B. Okay, so we will have the E squared D squared divided by 1 minus E squared. Okay. Still complicated, I think, right? But at least we have found the connections. Okay, found the connections. Let me write this is ellipse. E is less than 1. Okay, and then after we find these connections for the center H, A squared, and B squared, we can also connect to the relations with C and A and B. So C squared is just the difference on A squared and B squared. So we can take this and then we can compute this. Look, so we can write this A squared minus b squared. Okay, and then this will turns out to be e4 b squared, and then 1 minus e squared squared. And then we can take c in terms of e squared d over 1 minus e squared. And of course, this will goes back to our h here, right? The focus, right? The c is our focus, right? Remember, in an ellipse, you have an ellipse like this, and then you will have a focus here, and usually we are having c, right? So it confirms that our equation is correct. So this is negative h, right? And also, it follows that if we look on a squared and c squared is a squared, right? And c squared, it seems if we divide c to a, it will resulting e squared, right? The difference is only e squared. The other have the same terms. So we can also conclude that eccentricity is c divided by a. So that's the example for ellipse, and for parabola and for the hyperbola, you can also check. I think the easy one for parabola. For parabola, what you can do is your e is equal 1, right? For equal 1 from the, I think you can see from this side here. We have e equal 1. Okay. You can have for here e equal 1. This will be a 0, and it's going to be a perfectly quadratic equations for y squared, right? And for hyperbola, you can also imagine these equations. And then, if the hyperbola, then e is greater than 1. So 1 minus e squared should be less than 0 for that to be happening. And then we can get the hyperbola results. And instead of plus, we have a minus for hyperbola. Okay, it's the same process with ellipse, and a little bit difference on the terms, but it's actually similar. Okay, But the idea for this proving is we have to find out just this E is C over A. Okay. Okay. Now the polar in conics we can also describe in terms of general equations. Let me rewrite the equations in the new form, in the new page. Remember that at the beginning we have E and then D minus R cos theta, right? This is our first connections from the graph. If we solve this, and we solve with R, so we plus E cos theta, okay, and then ED. So we can rewrite this in terms of the general polar equations, which is ED divided by 1 plus E cos theta. Remember, this is to show that our graph will be on if this is directrix, this is the graph. Okay. So this is x equal d. This is f. Yeah, that's the graph. But is it parabola, ellipse, hyperbola? It depends. It depends. It depends on E. Because it can be an ellipse if you maybe draw and then make it like that. Or you just keep that as a parabola, or we have this and the other side. We have also. How to deal with this? We need to see whether E is equal 1, E greater 1, or E less than 1. So, for example, if we have the directrix on the left side here, and maybe the graph will be from here, here, and this is the focus around here, the right side. Can you imagine that? Okay. This will be negative, right? This will be negative. If we draw, let me just draw all the possibility of the polar. Okay, let's say this is x, but now we have a negative d, not d. And then we have a thing that's, this is f, this is negative d. The same way we deal with the previous problems, we have r here, and then we have this distance, blah blah blah, and then the conclusion is we will have that this will be ed divided by 1 minus e cos theta. So the pattern will be determined by, I think, the best way to look at these two conditions is the directrix on x equal d or x equal negative d. It will determine whether it's negative or positive. And remember, this is having cos theta. What's happened when we have this kind of curve? You get the cos theta is from here, from r cosine theta, which is the x, right? X in polar. If we have the like this one, two sides like that one, we will go through by we need to know this distance, right? And that is sine, right? Sine, okay? I hope you can imagine how it looks like, but let me just draw all the possibility. So this is two possibility for cosine. Say the first one is this Directrix, and we have the curve. Let's say a curve just like that. So the directrix will be y equal d in this case. Okay, this is the focus here, right? And our r will be equal, it's still ed. But now, instead of x, we will have y, right? Or if we draw here, we will have this triangle. So we are going to have this, right? So instead of r cos theta, we will have this is r sine theta. So we will have 1 plus e sine theta. Okay. And in the same way, when we have the directrix on the negative sides, okay, let's say that's our graph. So this is the directrix. This is the focus. The focus is all in the origin. So here we have r ed over e minus e sine theta. Plus minus, it came from the directrix. If the directrix is d, it will be positive. If the directrix is negative, then also the equation will be negative. Okay. And again, I think in polar, cosine and sine, they always have the same pattern, which is cosine is left, right, sine will be up and down. So first, we need to find, what we need to find is all the terms inside the equations, which is E and D. E and D. Let me give you maybe couple examples. Okay, let me give you a sample. Say R is equal 10 divided by 3 minus 2 cos theta. The question is sketch the conic So first, to sketch the conic, we need to find the E and directrix, at least those two. Remember that we have R, ED, this is 1, let's say plus minus, right? E cosine theta, or we have plus minus E sine theta. And we can look on, this is cosine, so we are using the cosine formula. So since R is 10 divided by 3 minus 2 cos theta, what we are going to do basically, we are going to make our formula back into the original equations, back into the 1 plus minus something, or 1 minus cosine, right? So we need to change this 3 into 1. So we need to divide by 3. So let's multiply 1 over 3, divide 1 over 3. This will get 1 minus 2 over 3 cosine theta. Okay. Now from here, this 2 over 3 is our E, right? Based on our equation E. So E will be 2 over 3. And the equations here is ED, right? And or we can write ED is 10 over 3. So D will be 10 over 3 divided by 2 over 3, which is 5. So our directrix is on 5, or x equal negative 5. So directrix is on x equal negative 5. Negative is from the equations, it's negative, right? So the directrix should be negative. And then how to find the values? We can use special angle if you want. So we can write R is equal Or we can check using just 0, pi over 2 pi, and then 3 over 2 pi. So we can check when theta is 0, r is 10 over 3 divided by 1 minus 2 over 3. This will be 10. And then let me just finish this, and then we can have short break. And r will be, this will be 2, right? And when theta is 3 over 2 pi, this is getting our same as the pi over 2, right? Okay. Okay, we can have a short break and we can continue. Okay, so let's draw the graph. So let's say the directrix here, which is x equal -5. So maybe this is, I need to take a little bit more, goes there. So this is 5, this is 10. Let's say this is 10, 10, 0. So 10, 0, we are going to rotate. So the graph is combinations of Cartesians and polar, or I would like to say the axis in Cartesians, okay? So, but the sections that we are going to draw based on the rotations in polar, okay? So first we start from 10, 0. Okay, let's just draw maybe like this. Or maybe I will draw directly and turns those into ellipse. I think maybe drawing a little bit more. Okay, maybe that's more like an ellipse. Okay, maybe that's our ellipse there. This will be the focus. And the other one will be, this is 2 and pi. This will be 10 over 3 and then pi over 2. This will be the 10 over 3 and then 3 over 2 pi. This one. Okay, as long as you mention the focus, directrix, and mention several points that indicates that this is the graph, I think that should be enough. This is E is equal to over 3. Okay. So if E is in between, let's say 0 and 1, okay, but not 0 or not 1, this will be an ellipse. And if you look at how the shape, maybe it will have like, it's almost a circle, but it's not a circle. And then it's more like an ellipse. And then imagine it's like a stretch and then take into a longer or elongated form. And then when it's equal 1, it's become a parabola. And when it's greater than 1, it has branched into 2 parts, become hyperbola. Okay. Okay, one applications of this this formula, or the polar in terms of conics, especially ellipse, is if you maybe learn something related to astronomical or astronomy, when you know that there is a planet, it's having an orbit, right? So if this is a planet, and maybe the sun is maybe around here, if this is R, and maybe let me write R in blue, and this is theta, we call the point perihelion, which is the closest to the sun, and the aphelion, which is the further from the sun, or the farthest from the sun. Now the distance, or the R, we can write in terms of these equations. Okay, so it's like it's an elliptical equation. So this is just an example, and just an example. So A is a semi-major axis. Semi-major axis A. Focus at origin. Eccentricity E, or E is equal eccentricity. And directrix is the D. So with directrix D, we can exchange to A. So D is equal 1 minus E squared. There are some basis for how do we define the semi-major axis, but I think I will not elaborate on this lecture. And yeah, I think this is just about it. The example. I'm not sure whether you're interested in astronomy or not, like planets, galaxy, or any theory about the universe? Not interested? Or are you mostly interested on new technology because you are using it every day, okay. Right? Or maybe you may be interested in topics like science fictions or maybe aliens. Maybe. Do you believe there is an alien out there? Or no? Do you believe? This is just I would just want to know. Do you believe it? No? No, because there is no scientific explanations, or maybe we are not really knowing yet, right? But interestingly, if you read some ancient texts or ancient artifact, there are some artifacts that still need explanations. That is, we call that out of place artifact. Like there is a clay. It's the age is maybe thousands of years, maybe 5,000 years. But when you open inside, it's like a capsule for battery, and you put some electrolyte, it still works. But most of the scientists, they prefer not to explain that because it's confusing, because why they have this but we have battery maybe at the 1-800 like volta, right? And there's several like artifacts that maybe we are not sure that we know everything. There's still some unexplored, okay? Like the topics like in the planets, galaxy, okay? But yeah, whatever. Because I think when I was still in your age, I was curious, like looking in everything, and then end up doing my my master and then my PhD. Okay, okay. I think the chapter 10 finished up until here. Okay, the part on the planet here is just an application on how we can use the polar into the polar in conic section in some applications in especially in astronomy. Let's move to the chapter 11. Let me. Okay. Okay, we can start with chapter 11. We will start with the sequences. Okay, we can start with a sequence or infinite sequence. We can really make into a list of numbers. Okay, list of numbers. List of numbers that arrange in some pattern or order. Okay, let's say it's A1, A2, A3, and then so on up until the some n, and still goes on if they still have some sequence. We call that this is the term, or this is first term, second term, and so on. I think you also already learned some about some of the sequences. we can also write the sequence in, usually we write in terms of having a bracket like this. Or we can directly write AN like that. Or having the conditions from 1 to infinity. But actually, just writing AN like that, we can know that this means that is a sequence. And we assume that n is started from 1. Sometimes it starts from 0, sometimes it's 1. It depends. Okay? Sometimes we can adjust from the given information of the questions, but the basic is all the same. Okay? Okay. If we have an is 1 over 2 with power of n, this means that if it is just stated, let's say, an like that, no mentioning from n equal 1 or equal 0, we assume that it starts from n equal 1. So we can write down that the an we can just write like that if we need to write the list. And there are several way to write. This is the simple one. We can also write maybe like n over n plus 1, and then n is from 2. We can take this and write in a list that is an will be 2 over 3, 3 over 4, 4 over 5, and so on, right? We can also write the pattern or the formula for n. We can include -1 with power of n, which is, it indicates that there will be some alternating signs. Sometimes it's negative, positive, negative, or positive, negative. Okay, so we can write this. Maybe we have these equations. 3 to the power of n. Let me write n is from 0, and then it's going infinitely amount. And we can write that the an will become, because it starts from 0, it's, of course, it starts from 1. Okay. And then the second one, this is having a -2 over 3, 3 over 9 positive, and -4 over 27, and so on and so forth. Okay. Now that is if we know the pattern, but sometimes we need to adjust the pattern by ourselves, or maybe you will be given some information about the numbers, and you need to maybe to look at the numbers and find out the pattern. Sometimes that will be the purpose sometimes. Okay, let me go through the next page and give you some example. I think this is already enough. So the question is asking what is the formula for AN. We can take this into terms that if you look at the signs, it's positive, negative, right? We need to start with positive and then after that negative. So we can think the signs came out from -1 with power of n minus 1 or n plus 1 if you start with n equal 1, right? Let's say we have negative n minus 1, and then n plus 2, and then 5 with power of n. So we will directly get that this will be, turns out to be 3/5 when you have n equal 1. And n equal 2, you will have 4/25, but negative. Okay? And so on and so forth. Okay? So I hope you still remember how to find the pattern. Okay? I think it's just play with some numbers and then see the patterns. There are some sequence that we don't really have some defining equations. Like Fibonacci sequence. This is recursively defined, right? With the conditions is to have these numbers. And we start from n equal or greater 3. So we have 1, 1, 2, 3, 5, 8, 13, 21, and so on. Okay, the next section is we can also think if we are looking at the AN is equal n plus 1, we can think this in the sequence from n equal 1, half, 2/3, 3/4, 4/5, and so on. If we graph this in terms of the distance that we are going to evaluate from the list of the sequence, let's say if we start from 0, and then this is maybe 1 here, and maybe half is this one, then this half will be A1, right? This is A1, A2, A3, and so on. Okay. A2 is 2/3, so maybe around this one. This is 2/3, so this is A2. A3 is 3/4, so maybe 3/4, maybe around here. A3. And then A4 is 4 over 5, maybe around here. Maybe around here, A4. And then when you increase your AN or your N, and looking at how the formula works, maybe it will be going to be when N, so as N getting larger, it will be closer to 1. So maybe it will be here. But it's never be 1, right? But it will be close to 1. Let's say N is, maybe N is 99. So AN is, or A99 is 99 over 100. So it's never close to 1. But it will be getting some slightly, like really a lot of numbers here colliding each other, or it's getting close each other, right? We can also, aside from this line number, that we can see how the sequence behave. Okay, how they can be get close to 1. We can also look at if we imagine with the Cartesian axis, let's y here becomes AN, and this x-axis become N. And we have some certain numbers, let's say 1, 2, 3, 4, 5. So maybe 10 is there. And then let's make maybe 1 here to make the graph obvious. And start from half, maybe half is here. Start from here, and 2 is maybe around here. 2 over 3, 3 over 4. And then when you have 6, yeah, I think I will stop here because the pixels getting closer each other, but you notice that it's getting closer to 1, right? And then by taking N sufficiently large, we can write limit as N approaching infinity, or N plus 1 is 1. In general, we can write down this limit and AN, and it will approaching a finite number L. And it's pretty much similar to what we learned in previous semester. So as N getting 0, AN will be close to L. And the terms in sequence, usually we are using if limit exists, we say converges or convergent, or convergent or convergent, we can also say. If doesn't exist, we say diverges. or divergent. Okay, to illustrate the convergence in limit, we can illustrate with some visuals. Let me draw. Let's say this is L. This is AN and N. Okay. Okay. Let's say we have maybe this is our value. We are going up, but then going down, and for the rest of the sequence it will be getting closer to L. We can also write this as limit n approaching infinity of AN is equal L. Although at the very beginning it start to increase like this, crossing the L, but then as the sequence increasing, the N is increasing, it's getting closer to this line now. And we can also say that limit as N approaching to infinity of AN is equal to finite number L. Or we may have some oscillations. Okay, some oscillations. It's oscillate, going up, going down. So we may have maybe from here going up, and then going down, and going up, going down, but then as N goes to really large to the right side, it's getting closer. So the oscillations that maybe the first visuals is maybe it's not having an exact number or getting close to which number, but it's oscillated, but then it's getting to some value that is L. This is also it's also converged. Okay, now what's the connection from the sequence to the limit? The connection is, in our sequence here, our N should be an integer, right? Our N is an integer. Like 1, 2, 3, 4, A1, A2, right? So N is an integer. So let me write here, N should be an integer. So it's actually the same concept as usual limit, but the function should be in the integer. The N should be an integer. Or if we write in terms of if limit, okay, f of x is equal L. This is the one that we already discussed in the previous semester. We can take the f of n as an, okay? And n is integer. Then we can say that limit as n approach infinity of an is equal L. Okay. And the limit law also apply within the sequence. I think you still remember. If you add the limit, if you take subtractions, if you multiply with a constant, multiply the two limits, and if you divide the limits, or let me write. So we can write limit. Maybe suppose an and bn both converges and c is constant. This is also applied for subtractions. This is also applied for subtractions. Maybe this is not really clear. This is the bracket. Okay. Limit c an. We can factorize c. It's a constant. Can multiply and you can divide. Also, you have another power law. P is positive and an is also positive. We can also have this theorem. If this is 0, then limit of the sequence itself will be also 0. And we can also apply the Squeeze Theorem. If you still remember the Squeeze Theorem. So in our case, it will become a tree sequence. So let's say we have an. So the first one is, let's say this is an. this is B. And this is the C. Okay, so n is greater than n0, and limit as n approaching infinity. So limit of an equals Cn equal L. Then the conclusions, the limit of Bn will be also equal L. Okay, same conclusions from, based on the Squeeze theorem. So basically, how do we find if we are going to evaluate the sequence when we are having the large n? Then we are just using the limit, and what we are doing last semester, we are just using as it is. Okay. So if we have a limit as n approaching infinity, n over n plus 1, what we do is, we know that this is similar to chapter 2 in calculus last semester, limits at infinity. So what we can do is look on, this is n, this is n. Basically we are going to divide both sides or both equation by n. So this will be 1 and 1 plus 1 over n, and we write the limit as n approaching infinity, and then this will be 1, 1, and then plus. If we are going to write completely, this is 1 over n, and this is equal 0, right? This one equals 0, so we are going to have 1, right? Okay. So basically, all the limit concept you have learned before, we are going to use all in our sequence to check whether the sequence converges or diverges. And of course, because this is limit, then we might have the conditions where the limit is, maybe this is f over g, and let's say that is we may have 0 over 0, and still we can use the L'Hopital directly. If you would like, you can also use L'Hopital when those happen. Okay. If we have an is just 1 minus 1 with power of n, if we check the limit, this is, we can have this negative 1 or 1, right? Depends on n. When n is 1, 2, 3, 4, etc. So it will be oscillated between 1 and negative 1. Therefore, the limit will be does not exist. Or we can say the limit is diverges. Diverge is spread out, right? converge is going to one focus, right? Now, if we have limit as n approaching infinity, let's say we still have this -1 with power of n, divide by n. We can check like what number this is. Maybe -1. Start with -1. And then half, right? And then -1 over 3, and then 1 over 4, and then so on and so forth. Can we take this limit and can we configure how to determine whether the limit exists or no? We can check the graph or the numbers, and we can see that it will going to be close to 0. Or if you look on the theorem, let me check the theorem. Where's the theorem? The theorem here. That is, if we going to check, we can check the absolute value of that an. So we can take the absolute value, and we may have, this is just 1 over n, which is 0. Okay, I think the last part is maybe, okay. Let me take the next page and having a last part of our course. So if limit and function f is continue at L, then so if we apply a continuous function to the terms of a convergent sequence, the result will be also convergence. Okay, I will just finish up now here, and we will go the rest of the sequence next Thursday, just maybe 30 to 40 minutes, and after that we will have some review on chapter 10. Next week, Tuesday, the quiz, okay, our quiz.